The Earth's interior is hot, and volcanoes are one of the places where the heat of the Earth is making its way out. When a volcano erupts, hot, melted rock called magma comes up from deep underground all the way to the surface. They are found all over the world, from Iceland to Chile to Lassen Volcanic National Park in North America. And each active volcano has a magma chamber underneath it. It's a place where new magma comes up from below. At the University of Nevada, Reno, volcanologist Philipp Ruprecht and graduate student Jakob Scheel are conducting research to learn more about the conditions leading up to volcanic eruptions.
Volcanoes have to be fed from new magmas from below, and that's what sustains a volcano, why it can survive for 500,000 years or 1,000,000 years to be in one place, because there's always new magma coming from below.
As the magma chamber gets recharged with new, hotter magma, some interesting things start to happen.
These two magmas have very different compositions, and as a result, they freeze at very different temperatures. And so when that hot magma comes in contact with the cold magma, it basically freezes. And under normal conditions, that means that it will turn into basically a solid rock. They can't be kind of mixed in easily anymore, right? Just like a chocolate chip inside a cookie dough.
This new magma, once frozen or hardened into denser, darker rock, become mafic magmatic enclaves. And they can tell scientists a lot about the conditions inside of a magma chamber in the time leading up to an eruption. Like whether there were different magmas mixing or how and when an eruption might occur.
We want to understand how magma chambers get changed prior to an eruption in terms of how they heat up before the eruption, how they potentially get more activated, right? And so we do this by looking specifically at one type of rock that is found within these domes, and those are called mafic magmatic enclaves. So rocks that are more magnesium rich, more iron rich, that's why we call them mafic. That typically means that they're coming from below, from deeper in the crust. These are new magmas that came into the magma body, triggered potentially the eruption, but also brought in new heat into the system and started to really warm up the magma body that then allowed for more mobility and more activity.
A string of eruptions happened about 1,000 years ago at Lassen Volcanic National Park and spewed magma and hot rocks to make up a series of dome-shaped volcanoes at the Chaos Crags formations. And that is now where Philipp and Jakob are looking at samples for clues about what conditions inside this magma chamber were like leading up to these eruptions. By taking samples from different sites on these dome volcanoes, they are able to see how this magmatic system may have changed over time.
We're looking specifically at crystals within these mafic enclaves. The crystals in many ways are taking note of the climate of the magmatic system here. So when the crystals grow inside this rock, they also are responding to any changes in terms of temperature. They will change their composition as a result.
By looking at the elemental makeup of the crystals, Philipp and other scientists are able to puzzle together the conditions inside the magma chamber leading up to an eruption. Here on the campus of the University of Nevada, Reno, they do this using an electron microprobe. This specialized piece of equipment works by bombarding the samples with electrons that then interact with the elements in the crystals in various ways, allowing them to measure their unique chemical composition formed in the magma chamber. The processes that occurred in the volcano caused the crystals to take up different elements as they grew. And depending on the elements they contain, these crystals will appear darker or lighter in the microprobe images. This allows researchers to better understand what happened in a magma chamber leading up to the eruption.
We can't drill into a volcano, and so as a volcanologist, we need to kind of get there by, for example, looking at crystals that basically were there at the site of where all the action happened. These crystals grow in the magma chamber, and as they grow, they keep record of what's going on as that magma changes, evolves, and ultimately erupts at the surface.
Philipp and Jakob are looking for two particular minerals next to one another in their samples.
Or we were trying to find specifically plagioclase together with another mineral, pyroxene. And those two minerals, when they grow together, we can use them to really target temperature in the magmas.
They can do this by using principles of physics, mathematics, and chemistry, and by using the microprobe to measure trace amounts of elements found within these mineral samples.
So we are really looking at the magnesium concentration in the plagioclase, and that plagioclase being in contact with another mineral, pyroxene. The pyroxene has a lot of magnesium, but the plagioclase, where we actually do our measurements, has almost no magnesium. And so the magnesium is going to move into the crystals at higher temperatures more easily than at lower temperatures. And so we can measure the levels of magnesium in this plagioclase and ultimately track that back to the temperature of these magmas.
So we're probing 6 different times basically what is inside of the magma chamber. And we can compare then our results of this evolution of almost ongoing eruption to different volcanoes that are in a similar settings. For example, volcanoes in Chile, Alaska, Japan, all where you find similar enclaves, for example.
Through their research and results, Philipp and Jakob are able to better understand the conditions in the magma chamber leading up to the eruptions at Lassen Volcanic National Park. And this research can help us learn more about the behavior of similar volcanic systems all over the world.